All right, welcome to the Explainer. Today, we're going to jump right into vector operations. This is the math you need to understand how to combine anything that has both a size and a direction. Like how does a pilot account for a crosswind? Or how do two people pushing a sofa figure out which way it's actually going to slide? That's exactly what we're going to break down.
I mean, think about it. If your boat's engine is pushing you straight across a river, but the current is pushing you downstream, you can't just add those two speeds together, right? That wouldn't tell you where you'll end up. You've got to account for those different directions. And the secret to doing that is vector arithmetic. And trust me, it's way more straightforward than it sounds.
Okay, so let's dive in. We're going to build your vector toolkit right now with just three core operations. And the best part? You master these, and you're pretty much set to solve almost any problem that involves combining vectors. So here are the rules of the game, and honestly, it's incredibly simple. When you add or subtract vectors, you just handle their matching components. You add the x's with the x's and the y's with the y's. That's it. And for scaling, you just multiply each component by whatever your scaling number is. No tricks, no weird formulas, just basic arithmetic. This is the whole foundation. Now, what's really cool is how this math looks visually. For addition, on the left, it's kind of like following a path. You travel along the first vector's arrow, and then from the very tip of that arrow, you travel along the second one. The result? It's just a straight line from your starting point to your final endpoint. And on the right, scalar multiplication is even easier to see. It just stretches the vector, shrinks it, or if the number's negative, it completely flips it around. Okay, enough with the theory, right? Let's actually see how this works with some real numbers. We'll start off easy and then ramp it up to a full-blown physics problem. So here's our first one. We've got two vectors, u and v. All we have to do is find their sum. Remember the rule? Just keep the components separate. And bam, here's how it plays out. We add the x components, so 3 plus -1 gives us 2. Then we add the y components. -2 plus 5 gives us 3. And there you have it. Our new vector is 2, 3. Simple as that. All right, let's kick it up a notch. This time, we're combining two operations at once, scaling and subtraction. So first, we'll scale up vector u by 3. Then, we'll scale up vector v by 2. And finally, we'll just subtract the new components from each other to get our answer. Okay, this is where it gets really interesting. In a physics or engineering class, you're not usually handed neat little components. You get something like this, a force with a magnitude, like 50 newtons, and a direction. The problem is our formulas need x and y components. So our first job is to use a little trigonometry to translate these forces into a language our formulas can understand. We use cosine to find the horizontal part and sine for the vertical. Now don't worry if your trig is a little rusty. The main idea here is that these are just the tools we use to break down each force. So that 50 Newton force becomes 43.3, 25, and the 80 Newton force becomes negative 56.6, 56.6. Now they're ready to go. And look at that. The second we have the components, we're right back in our comfort zone. The problem becomes easy again. We just add the x's together and add the y's together. And our combined or resultant force ends up being negative 13.3, 81.6. But what does that actually mean? Well, we can convert those components back into a symbol magnitude. And here's the amazing part. Even though we had a 50 Newton force and an 80 Newton force, their combined strength isn't 130. It's only about 82.7 newtons. That's the actual force you would measure. Now, before we move on, I want to point out a really, really common mistake. It's such an easy trap to fall into, but once you see it, you'll know to avoid it. Here it is, the big one. You can never, ever just add the lengths of two vectors together. I know, it feels like it should work, but doing that completely ignores their direction, which is, half the point of a vector. I mean, just look at the difference here. The wrong way, just adding 50 and 80, gives you 130 newtons. But the right way, the method that actually accounts for the directions, gives you 82.7 newtons. That is a massive difference. This is exactly why working with components is absolutely crucial to getting the right answer. So why does any of this matter outside of a math class? Well, let's look at a really cool high-stakes application where these exact calculations get used every single day: professional sports. In modern baseball, every time a batter hits a ball, tracking systems measure its velocity as a vector. And the very first thing analysts do is something called velocity decomposition. It sounds complex, but it's exactly what we just did. They just break that one vector down into its vertical and horizontal components. And here's the payoff. That vertical component tells them the ball's launch angle. Is it a grounder or a fly ball? The horizontal component tells them the exit velocity. How hard was it hit? By looking at just those two numbers, teams can predict almost instantly whether a hit is likely to be a home run or just a routine out. This has literally changed how hitters are coached and how teams build their strategy.
So that brings us to the end. We've seen that vector math is this super powerful tool for figuring out how things combine in the real world. So I'll leave you with this question. Now that you know the rules, what other things around you, from wind affecting a drone to currents in the ocean, could you understand just a little bit better with some vector math?